In our previous lecture, we proved that every radical Galois extension has a solvable Galois group. Today, we are going to prove the converse. If we have a Galois extension of Q with a solvable Galois group, then such extension is radical. So let us recall this theorem. So let E be a Galois extension of Q with a solvable Galois group. G. Then E is a radical extension. So that is, E may be obtained from Q by iterated procedure where at each step we adjoin n roots of some elements. Let n be the order of the Galois group, and let zeta be the primitive nth root of unity, so e to the 2 pi I over n. Consider a cyclotomic field K, which is Q adjoined with this nth root of unity. We are going to replace the extension E of Q with extension KE of the cyclotomic field K. We know that this extension is Galois, and the Galois group of KE over K is a subgroup in the Galois group of E over Q. Since we know that the Galois group of E over Q is solvable, we get that the Galois group of KE over K is also solvable because a subgroup in a solvable group is solvable. If we can prove that KE is a radical extension, then we immediately obtain that E is also radical. So for us, it will be sufficient to prove the following version of the original theorem. So let's call it theorem prime. Let K be a cyclotomic field where zeta is e to the 2 pi I over n. And let E be an extension of K, so be a Galois extension with a solvable Galois group G such that order of G is a divisor of n. Then E is a radical extension of K. Today we are going to prove the second theorem, and then applying the second theorem to the field KE, we obtain the statement of the first theorem. Before we prove this theorem about solvable Galois group, let us analyze the case when the Galois group is abelian. Theorem. Suppose characteristic of a field is equal to 0, and let E be a Galois extension of F with an abelian Galois group G, which is the Galois group of E over F, and we know that each abelian group can be decomposed as a direct sum of cyclic groups. Let n be the least common multiple of the orders of the cyclic components. and assume that F contains a primitive nth root of 1. So zeta is e to the 2 pi I over n. Then there exists element alpha 1 through alpha r in the field E, such that E is generated by these elements over F, and moreover alpha j to the power mj, where mj is the order of this corresponding cyclic component, belongs to the ground field F. So here, if we call by beta j the elements alpha j to the power mj, and so these are elements of F, then what we're saying is that E is obtained from F by adjoining nth roots of elements of F. So we'll get root of m1 from beta 1 dot 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 m r root of beta r. If we can prove this theorem, then we see that our main theorem with a prime holds in case when the Galois group is abelian. And we give a definition that extensions described by the above theorem are called Kummer extensions. Let us prove the theorem on Kummer extensions. Consider the dual group G star. So this is group homomorphisms from G to the multiplicative group of the field F. The elements of this group are group homomorphisms. These are functions on the group G with values in F star. Since these functions have values in the multiplicative group, there is a natural operation of multiplication of functions, where we multiply two functions pointwise. And then this set of functions naturally will acquire the group structure, and it's easy to check that the product of two homomorphisms is again a group homomorphism. Another term that is also used for this dual group is the group of characters. Of G. Let sigma 1 through sigma r be generators of these cyclic components of G. So sigma j to the power mj is equal to identity. We will use multiplicative notations for the group operation in the Galois group. Since each sigma has a finite order, under a group homomorphism to F star, it must go to mth root of unity. Then we get the following set of generators of the dual group. So this will be delta 1 through delta r, where delta j sends sigma j to e to the 2 pi I over mj, and all other sigmas are sent to 1. So clearly, if we take delta j and raise it to the power mj, then we get identity. And it's easy to see that the dual group is also isomorphic to zm1 plus zmr, where the deltas become generators that are dual to sigmas. Next, let us use linear algebra. So we know that each sigma j is an F linear operator on the space E. So here we view E as a vector space over F. And we know that dimension of this vector space is equal to the order of the Galois group. Since sigma j has order mj, so this tells us that as a linear operator, eigenvalues of sigma j are mjth roots of 1. And by our assumption, they are all in F. This means that we can bring sigma j to the Jordan normal form, but because these operators have finite order, they cannot possibly have Jordan blocks, because Jordan blocks will never give elements of a finite order. So from here, we conclude that each sigma j is diagonalizable over F. And we also know that these elements commute. So this tells us from linear algebra, we know that these elements then are simultaneously diagonalizable. But then the same is true for all elements of G. So if we take all elements of G, then they will be simultaneously diagonalizable. This means that we can find a basis of vector space E where all elements of the Galois group are represented by diagonal matrices. And it is clear that the joint eigenvalues are expressed by the elements of the dual group. Let us write down the eigenspace decomposition. So we'll get that E is equal to the direct sum over chi in the dual group of the spaces E chi, where E chi is the set of elements X from E, such that for all tau in the Galois group G, tau acting on X is equal to chi of tau times X. So elements of E chi are joint eigenvectors for all automorphisms from the Galois group, and the eigenvalues are given by the characters. The component that corresponds to identity element of the dual group is just this fixed point set under the Galois group G, so which we know is equal to the ground field F. In addition, we can see that here we have a grading of our field by the group of characters G star. So this means that if we multiply something in E chi with something in E phi, then the result will be in the component E chi times phi. Also, we know that if we have X in E chi and X is not equal to 0, then X inverse will belong to component E chi inverse. These properties are easy to check using the fact that elements of G are automorphisms of the field. Next, we state the following lemma, that for each chi in the dual group, the dimension of the component E chi as a vector space over F is less or equal to 1. Let's give a proof of this lemma. So suppose X belongs to this component E chi, and x is not equal to 0. And let us consider another element, y, in this component, E chi. We need to show that y is a scalar multiple of x. Now, consider x inverse times y. Since x inverse belongs to E chi inverse, and y belongs to E chi, this belongs to E with the identity component, which is equal to f. But then we can write x inverse y is equal to c for some c element of f, and then of course it follows that y is equal to cx. So what we proved, that any other element in E chi is a scalar multiple of x. So this means that E chi has dimension at most 1. As a corollary, we get that for every chi, the character in the dual group, the dimension of the component E chi is precisely equal to 1. We get this by simple counting. So we know that dimension of E as a vector space over F is equal to the order of our Galois group, and the order of the Galois group is equal to the order of the dual group. So in this eigenspace decomposition, we have that many components. Each component is of dimension less or equal to 1. So to get the right dimension of the whole space, we must take all components to be one-dimensional. Now let us return to the proof of the theorem about Kummer extensions. So let alpha j be non-zero elements in components E delta j, where deltas are the generators of the dual group. So here j goes from 1 to r. Then if we raise alpha j to the power mj, then we will be in the component E delta j to the power mj by this multiplicativity property. But these are identity elements in the dual group. So we conclude that alpha j to the power mj belongs to f. So if we take an arbitrary character chi, we can write it as delta 1 to the power s1 times delta r to the power sr. Then this tells us that alpha 1 to the power s1 times alpha r to the power sr. So this is a non-zero element in the component E chi. And this is non-zero because the field has no divisors of 0. So since our alphas generate all the components in this decomposition, we conclude that E is the extension of F with elements alpha 1, alpha r, and each alpha j to the power mj belongs to F. And that's precisely the claim of the theorem. Now let us return to the proof of our main theorem. So here we have a Galois extension of a cyclotomic field with a solvable Galois group. And we need to prove that this extension is a radical extension. So here let us consider the Galois group. And since this group is solvable, so we take the chain of commutator subgroup. So here we have the group G, which we will call G0. Inside we have the first commutator G1, then the second commutator G2, and so on. And after S steps, we will hit the identity subgroup. So this is the definition of a solvable group. Let us apply Galois correspondence. We know that to each subgroup we can associate a subfield. So to the largest group we associate the smallest subfield, K. Then we'll have a subfield that we'll call F1, then subfield F2, and so on. When we go to the smallest group, we will get the largest subfield Fs, which is our E. So this is done by Galois correspondence. We know that all commutator subgroups are normal in G. So we have that for every J, so Gj is normal in G. So by Galois correspondence, we know that the corresponding subfield, so Fj, is a normal extension, and thus the Galois extension of K. So we have that the Gj is the Galois group of E over Fj, and this is normal in G, J minus 1. Well, it's normal in G. And then this tells us that the Galois group of Fj over Fj minus 1 is isomorphic to the quotient of Gj minus 1 by Gj. And this group is abelian. And then, by the theorem on Kummer extensions, we conclude that Fj is obtained from Fj minus 1 by adjoining elements alpha 1 through alpha r, such that alpha I to the power mi belongs to Fj minus 1. So we get a chain of field extensions where at each step we adjoin several roots of elements from the previous field, which means that our field E is a radical extension of K. Now we proved the fundamental result that the Galois extension of Q is radical if and only if the Galois group of this extension is solvable.